Hi, we present towards learning neural representations from shadows, a new method that learns neural scene representations from only the shadows present in the scene. Traditional shape from shadow algorithms reconstruct geometry from shadows, but they assume a fixed scanning setup and fail to generalize to complex scenes. On the other hand, recent advances in neural rendering have enabled geometry to be learned from data. However, these methods rely on photometric consistency and texture information between RGB images and often ignore physical cues such as shadows, which encode valuable information about the scene. We observe that shadows are a powerful cue that can constrain neural scene representations to learn shape from shadow, and even outperform NeRF to reconstruct otherwise hidden geometry. Thus, we propose a graphics-inspired differentiable approach to render accurate shadows with volumetric rendering, predicting a shadow map that can be compared to the ground truth shadow. Even with just binary shadow maps, we show that neural rendering can localize the object and estimate coarse geometry. Our method can be summarized as follows. Given sparse binary shadow masks captured with varying camera positions under fixed lighting, and a proposed differentiable shadow rendering model that can perform shadow mapping, we learn neural scene representations. Our contributions can be summarized as follows. First, a framework that directly exploits physical cues like shadows and neural renderers to recover scene geometry. Second, a novel technique that integrates volumetric rendering with a graphics-inspired forward model to render shadows in an end-to-end differentiable manner. Lastly, results showing that our framework can learn coarse scene representations from just shadow masks. Our proposed pipeline is shown here. We train a neural network to predict opacity at points along the camera and light rays. The opacities are used by the volumetric renderer to output the ray termination distance, which we use to estimate the z-buffer from the camera and light perspective. The latter also known as the shadow map, which we'll talk more about later. The estimated z-buffer is fed into a projection step that projects the camera, pixels, and their associated depths into the light's reference frame. The shadow map is indexed to obtain their corresponding depth values at these new points. The projected depths and indexed depths go into a soft comparison step, which outputs the predicted cast shadows in the scene from the camera's perspective. A loss is then computed on the predicted and ground truth shadow mask. For more details, please refer to our paper. A key component to our method is differentiable shadow mapping, which allows us to create a forward model to render efficient and accurate shadows in the scene based on known light and camera sources. We define any point X in the scene to be in shadow if no direct path exists from point X to the light source. This logic implies that there must be some object or an occluding surface between the point X and the light source that occludes the light ray from reaching point X. This idea is known as shadow mapping, which we make differentiable using a soft comparison operation described in our paper, so it can be used in the neural rendering framework. Below are the results of optimizing our pipeline with the Atom Optimizer. A distance transform, similar to the one proposed in the UNET paper, is first applied to our ground truth shadow masks to weight them and make optimization smoother. As shown in this figure, as the model is trained, the predicted shadow mask and depth converges to the ground truth. The entire framework is optimized using binary shadow masks, and the MLP is trained on the loss shown here, the L2 loss between the weighted ground truth mask and the predicted mask. Shown here are qualitative results for 4 datasets rendered from Blender, comparing our method to the results obtained from the original NeRF paper, which has access to RGB images during training, whereas our method only uses binary shadow masks. Despite not using RGB images, our method is on par with NeRF. We note that the observations are taken from the bird's eye view of the scene, meaning the geometry of vertical surfaces of objects are only visible by looking at shadows, which is where we see the most improvement compared to methods that do not explicitly model shadows. Below are videos illustrating our results versus NeRF. The better reconstruction of vertical surfaces not in the line of sight of the camera is illustrated in the example of the vase on the right. We use root mean squared error to compare the predicted geometries to the ground truth and see that our method, which only uses shadows, is on par with NeRF for hidden geometries and vertical surfaces that are poorly sampled in the RGB space. Finally, we run our pipeline on a dataset of real-world images that were collected on the iPhone and optimized using coarse camera and light positions obtained by Colmap. Our method is able to accurately recover the geometry of the hand based on its cast shadow. Finally, we note that our method is robust to the sim-to-real gap since it only relies on binary shadow masks, which are the same in simulation and the real world. Thank you.